Thank you, thank you. Well, yes, I'm Steve Sagona. I'm working with Bill at OIST, and I'm going to give a tutorial on quantum memories. So this is meant to be a very quick, short tutorial on particularly ensemble-based quantum memories. You know, this is a summer school. I understand it's pretty advanced. A lot of people have strong backgrounds coming here, but I did design this for students who know quantum information, but maybe don't know atom-photon interactions very well. That said, since it is a strong audience, I've mixed in some advanced topics in the middle a bit and also at the end to cover more research level content. So let's begin with what is a quantum memory. This is a fairly overloaded term, but I'm going to give the most general definition, which is that it's a device that stores and retrieves quantum information. So you have a quantum memory, you have some quantum state, that information enters the memory, it stays inside of the memory, and then at some later time, you retrieve it. Sometimes the retrieval step is called the readout phase. So
can we ask questions?
Let's save it until there's quite a bit of content we're going to try to cover here. So why would anyone want a quantum memory? There's many different answers. Here are some interesting ideas. A memory, in some sense, can extend the amount of usable time that you have to work with. So if you have a processor and the coherence time of the processor is very quick, if you have a quantum memory that can store for a much longer coherence time, you can have some of your information stored in the memory and then quickly switch it over to the processor, process the information very quickly, and send it back to the memory. Another concept is RAM. So your computer has a large amount of memory in its RAM, random access memory, and in principle you can load that information onto the processor, and then with the limited amount of processors you can do some processing and then move it back to the memory. And this is essentially a framework where you could have a low number of qubit gates, but still be working in a very large Hilbert space, because you're moving things back and forth between the different memories, between the memory and the processor and back to the memory. Now, there's many different types and applications of quantum memories. Because of that, we're going to reduce the scope and we're going to focus on quantum memories that store quantum states of light. So this is a photonic quantum memory. Now we have a pulse of light. Pulse of light goes into the memory. It stays in the memory for some amount of time, and then sometime later, that same light pulse is read out. Now, let's stop for a second and ask, okay, but why are we talking about light-based quantum memories? What are they useful for? The main intuition, very simple. It's to control light and time. If we have two pulses and they're out of sync, we need to delay one to get interference. And that can actually be hard. So a naive way to do it, and the way that a lot of groups do it, is to have photons bounce in some kind of loop, either by having it go through a fiber loop, or by having it bounce around in something like a switchable cavity. Many labs use these types of, and you can call this a quantum memory. For instance, Paul Quaid's group has some very interesting papers where they have these very large switchable cavity systems. And additionally, Furusawa also likes to use these kind of switchable loop-based quantum memories. But they do have some very serious limitations, and that's basically that photons move fast. So if you have a photon bounce around in a loop, that loop needs to be really, really, really long to be able to get large time delays. So for instance, a 1 microsecond delay with a 1 meter loop, you'd be left with less than 1% of the light every time it bounces around. So, an alternative technology is to convert the light into another state and then retrieve that light at a later time. Many technologies can do this. This is rare earth frequency quantum memories and the spin memories. But even this, there's a little bit of a difficulty. which is that these memories, you store them into the memory, and then at some fixed delay time, they end up coming back out. That can be useful for some things, but for other things that ends up being problematic, because sometimes you actually need a custom delay. And if you need a custom delay and you only have fixed delayed quantum memories, then you have to do some kind of binary sequence of different fixed delays to be able to get what you want. If you need custom delays, then there's two techniques that can work. One's called heralded quantum memories, or like the DLCZ protocol, and then the other is what's called on-demand memories. Heralded memories is probably what most people here are familiar with. Nico is also going to be covering this topic in the future, so I'm just going to quickly cover my base here and just sort of overview what a heralded memory is. It's a bit different than some of these other memories. It does not actually store and retrieve light. Instead, the light is used to know if a quantum process has occurred. So for instance, you start with a system that can decay. So for instance, you have a quantum state, it's in some excited state labeled 1, and there's no photon that comes out, and it can, for example, decay, change to a 1 state, and then a photon comes out. So if you get a click on your detector and you see a photon, then you know that your state is in a 0 state. Then what you can do is you can kind of mix and match these by having multiple quantum processes. And then what you do is you mix the which way information of these two photon pulses. And as soon as you get one click, you know that it either had to happen in process A or in process B. And because of that, because we don't know which, these processes end up being entangled. This is the intuition behind what's sometimes called the DLCZ protocol, where you're transferring the information through the entanglement that's stored inside of the medium, as opposed to the light itself. Now, this will be covered in more detail by Nico in a later talk. There's another technique where you can get custom delays, and that's an on-demand quantum memory, which we're going to focus on here. An on-demand quantum memory uses optical pulses to trigger the storage and retrieval events. So an on-demand quantum memory, you have a light, the red you want to store. The purple in this case is the strong control field. You read it into the memory. And then later, when you want a very specific timing, you send the strong control field pulse, another strong control field pulse, and that causes the red pulse, the stored pulse, to be able to come out of the memory. The advantage for this is that you can send in a control field pulse at whatever timing you want, and then you get exactly the signal that you got stored into the memory for that custom timing. In addition, there's also some other unique applications that you can have for this type of memory. These memories only store single temporal modes. So for example, if you send 2 Gaussian pulses into the memory, you'll store the Gaussian pulse if the control field is a Gaussian pulse. You can also do this for a different type of temporal mode. If you make them both Hermite-Gauss modes and you send them in, you'll also store into the memory. However, if the probe field is not matched to the temporal mode of the control field, if they're orthogonal to each other, it won't store at all. So if we have a Gaussian and we try to store using a control field that's HG1 mode, nothing happens, no store. So this is a type of temporal mode filtering, where in essence, what you can do is you can actually even send a superposition of a Hermite-Gauss mode and an HG0 and HG1 mode. And then if you use your control field matching one of those two modes, you can filter out that particular mode. So this can function as a temporal mode detector. And our group has, at my old group at Imperial, where I did a postdoc, showed that this can be better than the classical limit. So in principle, if you end up sending 2 very close Gaussian pulses to each other, you can use this technology to project that in a Hermite polynomial of HG1. And that projection operator, you can resolve those 2 pulses better than if you just were trying to resolve this with typical Gaussian pulses or with the photodetector. Sometimes this is called super resolution. So we can also reshape the stored photon by reshaping the control field. So we store the photon into the memory. That's the read-in phase. But then what we can do is we can choose a different readout control field pulse. And then what was stored in the memory, no matter what it was stored in the memory, will come out as the new readout control field pulse. So this also allows you to be able to change different temporal modes from your system. So it's not just a filter, it's also can do temporal mode conversion. And it can even do basis conversion. A little bit out of the scope to go through exactly how this works. But this was, the preliminary experiment for this was done in collaboration with University of Warsaw, and circled in red here, this is Yerzha, who's also here with us today. He's great help in setting up the experiment. It was basically me and him just working on it for a long time. These are some experimental results. I'm not going to go too into detail about this, but basically it's showing that if you send in a superposition of 3 different Hermite-Gauss modes, then you can end up with 3 pulses of normal Gaussian light that comes out that are time separated from each other. This is basically a basis conversion between one type of degree of freedom, Hermite-Gauss modes, which are particularly good for things like quantum pulse gates, to a pulse train of Gaussian time-separated bins, and this is sometimes useful for light traveling down fibers. So we've covered what applications are useful, but how exactly do these memories work? What's the physics? So I said that this talk is to attempt to cater to some who've maybe not seen that much AMO physics. So we're going to review from first principles some basic light matter interactions. And in particular, we're going to do this with relevance to room temperature ensemble-based memories. So in this case, we store the state of the light inside of a warm vapor gas of rubidium atoms, just typically in a little glass cell that's this big. Inside of this cell, we have individual gas atoms that are bouncing around. For rubidium, this can be modeled as basically just being a nucleus core and 1 valence electron. Now, when an electric field is applied, this electron can move to a superposition of energy states. We can find out how much it's in a superposition by doing the optical Bloch equations. So this is basically just setting up what the standard Hamiltonian is. And for a 2-level system, I'm sure most people have seen this before at some point. An electron can be put into a superposition of eigenstates. And when that happens, it creates a dipole moment. That dipole moment then affects the electric field. This then is another type of differential equation. So this is Maxwell's equations done in the slowly varying amplitude approximation, where you just assume that you basically just paying attention to the envelope of the pulse. In this case, the polarizability term is actually proportional to the dipole moment, and that dipole moment is proportional to the amount that the electrons are in superpositions. Most light matter interactions can be reduced to these 2 coupled set of equations, the optical Bloch equations and the Maxwell-Schrödinger equations, which in essence is a system of ordinary differential equations that's coupled to a PDE. Now, that's not so intuitive, so we can go beyond just 2-level systems in one field with these equations. And maybe the best way of doing this is by looking at some simple examples of what happens. So as a reminder, of course, everyone's going to know this, but if you take a strong field and you send it through a 2-level system, some of the atoms are going to get excited. And then after you wait some amount of time, those excited atoms are going to end up decaying back into the ground state. Now, everyone knows that. Let's move to a 3-level system. in an experiment, of course, we don't have an exact 3-level system, but we can model it by saying that our lasers are at least closest to resonance near 3 of the levels of this more complicated configuration. Now, if just one of the 2 levels are on, then it leads to this effect called optical pumping, which is very important. So if I leave a field on and it's on resonance with the excited state, that state is going to be driven back and forth. Some of the time, it's going to go back to G1, and some of the time it's going to be sent to the other ground state, which is not on resonance, which means that eventually at steady state, all your population is going to accumulate into the other ground state. This is called optical pumping. It's often the first step of quantum memory. It's extremely important because you need to prepare your initial state in the right way. And also, lots of papers investigate basically how much energy you need to be able to do this, how hard it is, and the more atoms you have, the more energy and time you need to do this. Now let's consider another example. We have both of the fields on at the same time. Now, no matter where it starts out, if you run at steady state, you're going to get a 50-50 distribution between the 2 ground states. Quantum mechanically, we can also think of this as a superposition state, not just a statistical mixture, where we're simultaneously in the atoms are simultaneously in both of the ground states at the same time. So then you can ask now the question, okay, instead of having 2 strong fields, I have a strong field and I have a very, very, very weak field. So weak, it's a single photon. What happens in that case? Well, you still get a superposition state. It's just that the amount that you're in B, in this case, is basically 1 atom's or 1 photon's worth of pushing in that direction. So you have 1 photon's worth of excitation in the second ground state. The reason why that's helpful is that this is what we're going to use to do storage of light with the Lambda system. So the protocol for storage is as follows. We send in both of the 2 fields. We send in our single photon and our strong control field at the same time. That prepares us in this special superposition state, which just has a little bit in B. Then both of the 2 fields we turn off. There's no photon, there's no control field. Now it's stuck in the ground state. Both of these 2 states, A and B, are ground states. B cannot decay into A. So in this circumstance, it's stuck. And this is in essence why we can end up using this as a memory, because it has a long coherence time. Then finally, in the readout stage, when the control field is turned on again, we can end up turning that superposition back into photons. Now, life is more complicated, so having an ensemble of atoms ends up increasing the probability that a photon ends up being stuck into the memory. But it also adds complexity. So when you store a single photon with many, many, many atoms, it's very likely that it's actually going to get stored up in the front of the cell as it's entering the cell. So what that means is that if you were to look at how much the state is in a superposition of the different ground states, you're going to see that the very front of the cell has a different amount of superposition than later in the cell. And this property is sometimes called the spin wave. It's also called by a number of different names. So when the system is on resonance, it's called the dark state polariton. It's one of the first inventions of it. When it's far off resonance, the spin wave is called the storing in a Raman memory. And at high power, it's sometimes called the Outler-Towns memory, Outler-Towns splitting memory. On resonance, quantum memories are good at storing slow pulses. So EIT-based lambda systems are good at storing slow pulses. And these slow pulses end up having high internal efficiency because it's close to resonance. And this was the main thrust of my old PhD group in New York with Eden Figueroa, and that's where I got my PhD. Thakkol's lab was to achieve distributed quantum entanglement through room temperature EIT memories. The advantage of these memories is that they're very cheap. So you could imagine having a distributed set of these nodes. And this, for instance, is a a paper that I helped out with where they were looking at the two spatially separated quantum memories. And this was the first time that Honga-Mandel interference was done between two separated memories to try to compare essentially how identical the memories are in the process. Because, of course, the memories also now need to be identical and not just the photons themselves. This lab also has had two labs, one in Brookhaven National Lab and one in Stony Brook University, and work has been done to create a long-distance, quantum-capable, quote, internet testbed, where basically telecom fibers are connecting two different labs, and efforts are being made to fully set up networking capacity with this with these memories. Now, far off resonance memories, the spin waves that are sometimes called quantum Raman memories, or storage with Raman memories, typically have lower efficiencies, but can operate at much higher bandwidth. This major focus of Ian's group, Ian Walmsley, I worked with him at Imperial, but he went from Oxford to Imperial, and now he's back at Oxford, where I did a postdoc. And the advantage of off-resonant memories is that they have they work very fast, and they are, in a lot of sense, the most compatible memories with quantum dots. Quantum dots are very fast temporally, so they have very broad bandwidth. So the fact that you're very far off resonance makes it a lot easier to work with these fast pulses. So, for instance, we were the first group to store quantum dots in a telecom quantum memory. This was an ORCA configuration. If there's questions after this, I can explain the difference between ORCA and a Raman system, but it's basically a three-level system where one of the levels is stuck at the top. Now, so we've covered a lot of the different applications for these types of memories. There are a lot of challenges working with these types of memories, a lot of efforts to sort of beat these challenges. So I want to just kind of very briefly overview the different types of issues that these memories have and what people are thinking about in terms of fixing it. One issue is frequency filtering. So because these are two ground states, what that means is that the strong control field that is only something like 10 megahertz away from the other transition. So even if there are no other noise terms, what that means is that you need to be able to separate your signal field and your control field by a very large amount. So these are co-propagating fields, and you need to be able to frequency filter these two fields apart, but they're only separated by 10 megahertz. Polarization filtering is the first step that can get you something that can give you some amount of filtering, but since this is a very strong control field and you want to be able to store single photons, you need very, 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 very high degrees of filtering. So because of that, and because these frequencies are so close, you need to use etalons. These etalons are oftentimes very lossy. And because of that, the input-output efficiency of this system, when you take the entire filtering into account, oftentimes you lose 90% of the light in this step. Even with that, there's an even more deadly problem, and that is noise. The most common noise that a lot of groups have focused on trying to defeat is what's called four-way mixing. It's called spontaneous four-way mixing, and in essence, the control field accidentally couples to the other transition off resonantly. That causes a scattering effect due to anti-Stokes scattering, and then the control field then re-picks that back up, and it comes out in the frequency of the probe. This is a really bad form of noise because it also affects the fidelity of the measurement. Because what it's saying is that even just with the control field on, you're going to have light that comes out in the frequency of the signal. Almost for 10 years, this was the main problem of getting quantum memories to be at the single photon level. And there's a number of different techniques that have been invented. All of them work. This is one by Ian's group that ends up working as well. And in this, to sort of summarize it very quickly, what you do is you intentionally choose the off-resonant condition of your memory such that the anti-Stokes scattered light ends up being absorbed by one of the line widths of your system. And when you do this, you interrupt the four-way mixing process in the middle of it. You prevent it from being able to fully go through this system. And in effect, this very dramatically reduces the four-way mixing noise. Normally you red detune your light, and this is a blue detuned system. So we still have plenty of time, actually. So now we're going to go into some of the more research-based topics. But maybe let's take a pause here and just see if there are any questions. Yes?
So you mentioned that the longer memory has higher bandwidth. So does that mean you can save different frequency?
Does it mean that you can work with multiple frequencies? Are you asking if you can do multiple frequencies at the same time?
Yes.
So that cannot happen for the reasons stated here. Where is it? Okay, well, instead of getting to the slides, the memory is single mode. So basically that means for every control field that you have, there is a sort of optimal signal field that can store it. You can't do, there's no free lunch, you can't do multiple things at the same time. Let's see, any other questions? Yes? Yes.
That's actually an issue, or in case if you can about the same, especially labor, most likely shaping the distribution.
I've never heard anyone ever suggest shaping the atoms. I guess for a MOT or something where you have laser control of it, then that might be an interesting idea. I mean, it's also interesting for the room temperature stuff, but I've never heard of that. So the typical way that you try to defeat this problem, well, first let's talk about, so I didn't mention actually why, I just said that this is a sort of an extra technical point. I didn't say why this ends up becoming an issue sometimes. There's two different reasons why this becomes an issue. One is that if you send the control field in the opposite direction, the phase of this spin wave ends up being mismatched to it, and you can't get the light to come out. So basically, when you do reverse directions of this, you end up with kind of like a phase matching problem that happens. That's one type of issue. You, of course, can send it. There's always a sort of correct direction you can send it, and then it's not a problem. However, another issue is that if you have a really, really, really efficient memory, where you're absorbing something like 80% of the photon, then what that means is that the photon is going to end up having a high likelihood of being in the front of the memory. And that sounds great. Well, why is that a problem? Well, when you try to get that light back out, what's going to happen is as that light comes back out, it has to now travel through this very dense memory again, and it will just end up getting stuck back into it again. So you end up with this diminishing return in terms of efficiency that happens a lot of time due to bunching of the spin wave in front of the memory. Now you can fix that by doing control field shaping or some things in the extra credit section.
So can you make the equation backward so that you don't pass through the density?
It depends on the configuration of the system. For lambda systems, you need the light to be collinear for this spin wave phase matching to work. But for this other scheme, which I did not cover in great detail, for this scheme, the ORCA scheme, the only way that you have the correct phase matching term is actually in the counterpropagating scheme. So this scheme actually succeeds in being able to not have this issue. And with this scheme, you also can skip the etalon step as well, because these two frequencies for this type of configuration are not very close to each other. So you can end up with wavelength differences and you don't need the etalons anymore for filtering. The problem is that now this is at an excited state. So if you store it for a long time, you want to hold on to it for a long time, it's just going to decay. Okay. Now for some of the fun stuff. Why are light-based quantum memories useful? How do they work? We cover these things now. How good do quantum memories need to be? So if you've noticed, there's lots of different types of quantum memories that, that we've covered here, just even for just lambda systems. And what you notice is that sometimes there's just trade-offs. So you make your thing off resonance, you make your efficiency worse, but you improve the bandwidth. Other times you end up making your efficiency better, but you decrease the fidelity, right? And you know, it just might be that there's just not enough free parameters to be able to get what you want, right? So there's a question of, you know, maybe is this even just a fundamental, these trade-offs are just fundamental, right? Also, even just for a single figure of merit, like trying to improve the efficiency, a lot of these memories end up require exponentially more resources. So for instance, for the Raman memory, to be able to increase the amount of efficiency, going from 80 to 85% is much easier than going from 90 to 95%. So you need exponentially more resources to get all the way up to these large numbers. And you could imagine that when we're trying to think about applications like it being a quantum memory, where we're storing it like RAM, we want this to be as efficient as possible in maintaining the quantum state. Ideally, you know, 99.99 along those lines, right? But the problem is that, you know, quantum memories right now just aren't efficient, and then there's, you know, you have to make serious trade-offs even to get them to be highly efficient. But that said, it's not that hard to make a 50% efficient quantum memory. If you look at the light pulse, then you see that basically what ends up happening is that when you store the light pulse, some of the light pulse ends up not being successfully stored into the memory. Some of the light pulse is successfully stored and is retrieved with some delay. So this is a typical picture of what the what it would look like in a lab when you end up storing and retrieving light. So that's the retrieved pulse. This is the light that failed to be stored. But if you notice, they're both there. And if this was a photon, you would actually say that this stored light and unstored light are in a quantum superposition. You know, if you know Mach-Zehnder interferometers, what you can do is if you have a 50-50 beam splitter and you send a photon through a 50-50 beam splitter, you can create a Mach-Zehnder interferometer, and then by playing around with the phase, you can deterministically force a single photon to travel one of the two paths through the system. So we can use quantum interference for optical paths to be able to, we can use quantum interference to make a 50% efficient beam splitter become 100% efficient by playing around with the phase. So similarly, you might think, okay, well, can we do some kind of optical interference of these two pulses and try to interfere them so that this 50% efficient system becomes 100% efficient? Yeah, you can do that, but it's a bad idea. The reason why it's bad, basically, is that in order to be able to interfere these two things optically, they're separated in time. So to be able to get them to interfere optically, you need to now get a quantum memory or some kind of delay to be able to bring them back to the same sort of temporal space and interfere them. And the whole point of this was to create an efficient quantum memory, but you need an efficient quantum memory in order to be able to do this. So it doesn't work. But there's a there's another thing that we can do, and that's by identifying that this process of storing into the quantum memory, you can think of as a linear beam splitter model, where you're mapping the single photon state into a superposition of having been stored into the spin wave and also being unsuccessfully stored and staying as a photon. So this ends up being exactly like a linear beam splitter model. So by an analogy, to be able to get this quantum interference to happen for a beam splitter, what we can do is we can send it through another beam splitter. We can then ask the question of, what would that look like if we had a memory? So the thing to remember is that our spin wave is not a traveling wave anymore. It's staying inside of the memory. So how do we do a sort of Mach-Zehnder-like interference where one of the degrees of freedom is staying put? And the way to do that is by looping the pulse back around the front and then trying to repeat the storage process a second time. And when you do this, now you have the analogy of a quantum Mach-Zehnder interferometer, but you're doing quantum interference between the stored spin wave and the photon pulse. So what's great about this is that you can take a 50% efficient memory, you loop the unstored pulse around, and then when you try to perform a second storage step, you can change the phase of the photon pulse that's entering, or the phase of the control field, and that will deterministically control if it is fully stored or fully retrieved, just like a Mach-Zehnder interferometer controlling the outputs of the two beam splitters. So you get a 50% efficient memory, and then theoretically you go all the way up to 100% efficiency. So we avoid all these nasty trade-offs with trying to increase the control field or playing around with the parameters. And 50% storage efficiency memories are dramatically easy, orders of magnitude easier to use relative to 100% efficient memories. Not only that, but there's two steps to a quantum memory. So the first is the storage step. So that has an efficiency. And the retrieval efficiency, the retrieval step also has an efficiency. So you can do this protocol twice. You do the beam splitter analogy for storing the light into the memory, where you loop it back around. That takes your 50% efficient storage or read-in efficiency to 100% read-in efficiency. Then you repeat this for retrieving the light out. What happens in this case is a little bit different. You can think of it like a Mach-Zehnder interferometer with a different arm as the input. In this case, you try to retrieve the light. Now there's still some spin wave that's stuck inside of the memory. You take your photon, you loop it back around a second time, and then when you send it through, this time, when you play around with the phase, now you can force all of it to come out. Now, this in an ideal world would say that 25% total efficiency can just bring you up all the way to 100% total efficiency. But life's not that simple. It is a linear relationship between these two things, but you do still have to take into account the fact that this is a spin wave and you have a pulse. And the combination of these things ends up being this kind of complicated Green's function solution, which requires that you need some sort of pulse shaping to get the optimal. So the analogy is a little bit blurred due to the effect of the spin wave, but we did the theory, we did the experiment, and we showed that basically if you do pulse shape your pulses, then with this protocol you can boost the Raman memory all the way up from something like a 60–70% memory all the way up to 98%. And this is with doing optimal pulse shaping both for the Raman and for the this interference step as well. So there's no, it's not just due to the pulse shaping. We're fundamentally improving the total efficiency from this protocol. From this calculation, you see that we end up requiring 16 times less power. I think that for the more extreme, this is in the case where we have fairly low efficiency, but If you needed that ROM in memory to go to very high efficiencies, the amount of power you'd be reducing here is way more than 16. And then additionally, because we're not using the same strength of the control field, because we're using orders in magnitude less strength of the control field, that means that we reduce on these noise terms as well. A lot of these fundamental constraints of that are tied together, we can break through a lot of these difficulties. This is an example of an experimental setup for the ROM in memory. Feel free to ask questions after, but we did this experimentally, and for the first step where you tried to do a improvement to the reading efficiency, we see a significant boost from 40 to 70% reading efficiency. It ends up not completely improving the total efficiency, and that's due to the bunching of the spin wave up in the front. You can also then do it for the second step, for the retrieval efficiency, and you get a significant boost in the efficiency as well for this step, and then you can combine the two. And in this example, we observed experimentally that you can go from a 10% efficient internal memory total efficiency to a 30% efficient total efficiency, and this is without any pulse shaping. So we know theoretically that we can get all the way up to 98, but this is just kind of a first step to show that the concept works. This was published just recently, I guess about a month ago in Optica. And we saw that we had a threefold improvement in total efficiency. I think it's quite a cool conceptual idea, using quantum interference in a more abstract way. And hopefully is a sort of good overview of quantum memories in general. So thank you for listening, guys. That's it. Yeah. If there are any questions, yes?
So for this EEI storage to work, you have the superposition of being stored and not being stored. So if the full get lost,
yeah, so the efficiency of this loop has to be extremely efficient. In this case, our loop efficiency was actually only something like 50% efficient, and we still got these good numbers. And part of that is that it's the square root of efficiency that's dealing with the probability amplitudes that you're working with. So actually, you have a bit more play than you think you would if you're thinking about efficiency.
But are there any, with this ESP, are there any more stringent requirements on how far you can shape the pulse fields
Stringent requirements on shaping the pulse field. So we did this strictly numerically for seeing this observation of the improving the total efficiency. So I don't think we've built an intuition yet for sort of why we need certain pulse shapes. So I think that hopefully will come later.
So
yeah, exactly.
Thanks.
I will ask a prominent question.
Yeah.
Your first slide said that a memory is any device. We have input, it stays there for a while, it comes out. So what's the difference between a quantum memory and a quantum processor? I have an input.
It's a quantum processor that has the identity operation. Would
yeah,
be
exactly.
Yeah. Yeah. All right. Thank you.
That's what it's time to speak again.